Hello, everyone. Good morning, good afternoon, wherever you are in the world. Welcome to our webinar today. My name is Thomas von Lacher. I'm Managing Editor Engineering of the journal SN Applied Sciences, and I had to run the meeting today. Today we have Professor Tomáš Bodnar from Czech Technical University in Prague with us. Welcome, Tomáš. And I would like to introduce Professor Bodnar. Professor Bodnar received a master's degree in aeronautical engineering in 1998 and the PhD in mathematical modeling in 2004, both from Czech Technical University in Prague. In addition, he received a master's degree in mathematics from Charles University in Prague in 1999. And from the University of Toulon in France, the PhD in Sciences de l'Univers. Today, Professor Bodnar is Associate Professor at the Department of Technical Mathematics at the Faculty of Mechanical Engineering at the Czech Technical University in Prague, as well as researcher at the Institute of Mathematics at the Czech Academy of Sciences. And I should not forget to mention that Professor Bodnar is guest editor of the journal's topical collection, Recent Problems in Fluid Mechanics. So back to our webinar today. We will have time for questions after the talk. So please type your question into the chat box as we go, or after the talk, you can unmute yourself and ask your question. So with this, I hand it over to Professor Bodnar. Tomáš, again, we are delighted to have you in our webinar series today. And the floor is yours.
Thank you very much, Thomas, for the nice introduction and invitation to give this talk. I will try to share now my screen with my presentation here. Okay, let's try. So it should be visible now.
Yes, it is visible. Looks very good.
Well, let's try if the presentation mode will work. Can you see it?
I think this is a presentation mode, yes. Yeah.
Okay, so as announced previously, my talk should be on some computational challenges in numerical simulations of stable stratified flows. Again, as Thomas mentioned, I'm coming from the Czech Technical University where I'm sitting now. And I also partly work in the Institute of Mathematics. So also the talk will be partly, let's say, engineering style with some flavors of mathematics. So this is the schedule of the talk. First, I will briefly introduce the mathematical model for stratified flows. Then we will run into some phenomenology of these kinds of flows, and we will introduce some of the first problems that we can find in this kind of flows. Then I will go in more detail through the numerical methods that I was using in simulations of these flows. Then we will discuss a physical example of flow over a hill, where we will show the remaining part of the phenomena and of the problems that we are facing in the numerical simulation of this kind of flows. Based on this discussion, we will run into a problem of far-field boundary conditions for stable stratified flows. A new proposition for far-field boundary condition will be introduced. And finally, we will end up with discussing this new boundary condition. So this is the plan. As you may see, it was scheduled for 54 slides, so it's quite a lot of material, so I will sometimes pass through it a bit faster. So this is the mathematical model that we are using in our simulations. It is based on incompressible flow equations, but with variable density. So as you may see, in contrast to some oversimplified definitions of incompressible flow, here we deal with incompressible but variable density fluid. So this system is called the non-homogeneous Navier-Stokes equations. You can find it in the classical mathematical book of Lyons, for example. So this is the basic part of our consideration. So in addition, what is here more, what will be important is this term, including the density and gravity acceleration. Otherwise, it's standard fluid model for the velocity field, pressure field, and in addition to standard homogeneous incompressible model, here we will have a field of density. This model can be partially simplified by just removing the hydrostatic pressure from the model. So it means we decompose the density and pressure fields into some background part that only depends on space, and some perturbation that can depend on both space and time. In this way, we can really relate the background density and background pressure by this hydrostatic relation. This is just a very common approach to remove the hydrostatic pressure from the equations. So here we will deal with just pressure perturbation in the pressure gradient term, and we will also subtract it from this buoyancy term that depends on gravity. Also here, just the perturbation with respect to background field will play some important role. But what is important to mention here is that so far the system is complete. So we did just some decompositions and some rearrangements, but otherwise we made no approximations. In fact, the only approximation that we will do in this system is in the density. It's classical to use the so-called Boussinesq approximation, which means that instead of the full density that was mentioned previously, we will use some characteristic density here in the convective term, while the variable density will only play a role here in this buoyancy term in the momentum equations. So the whole system can be written in two different ways. First, in this way, where we have the transport equation for the full density, and then we have the balance of momentum, where we, in the convective term, we only play with the constant like characteristic density, and the variable density is only represented here with this density perturbation rho prime that is on the right-hand side as a buoyancy term in the momentum equations. Alternatively and equivalently, you can rewrite the whole system using the density perturbation only. So you will get again some kind of transport equation for the perturbation with some source term that depends on the vertical velocity component and the background density gradient. But otherwise, these two systems are really equivalent. It's just a rearrangement. And the only simplification is that instead of the complete density here on the left-hand side, we are using some characteristic value. Otherwise, again, it's really just the only simplification here. This kind of governing system has some very important features and describes a very important physical phenomena. Here, this example is mentioned here as one of those that we will solve later numerically, where, for example, if you have flow over a hill, then in the standard incompressible Navier-Stokes-like model, without the variable density and namely without the stratification, the flow will just it will just flow around the hill, and here behind your streamlines will reattach and will go almost parallel to the surface again. This is in contrast with what we will observe in stably stratified fluids and flows, where by this excitement through the hill, in the whole boundary layer, you will observe the wavy pattern. So you will not have like simple flow structure as you are used to from non-stratified flows. This wave structure can be characterized by the so-called Brunt-Väisälä frequency, which is denoted typically by n, and you can see that it depends on the background density gradient. So again, if you will have constant density, then this background density gradient will be 0. And then it depends on the gravity acceleration. Here in all the following slides, everything will be formulated using density. But for example, it's typical in the atmospheric science to relate the density with temperature. So here everything can be written using the potential temperature theta instead of the density. What is important is that this buoyancy frequency, the Brunt-Väisälä frequency, leads to generation of some waves where the wavelength of these waves is somehow proportional, inversely proportional to this frequency. And you will see that increasing the velocity will also increase the wavelength of these waves. So this is the basic kind of phenomena that we will observe in the stably stratified flows, and that will distinguish the cases solved here in this model from what you typically know from the, let's say, engineering fluid mechanics. Here, I'm presenting one of the first examples of such kind of flows. It's kind of a laboratory experiment where you have some tank with stably stratified fluid. I think in this case, it was water with salt. You can find the details of this experiment in these publications by Yuli Chashechkin and his co-workers from the Academy of Sciences in Moscow. And what they do is they have this tank filled by a fluid, which has this, what we call stable stratification. So it means there is some background density profile where naturally the heavier fluid is close to the bottom and the lightest fluid is on the top. And then you have a horizontal strip of virtually 0 thickness that is moving in this tank and let's say disturbing this steady and stationary density profile. So here we had some computational domain where here you have the strip that is moving horizontally in the fluid. So we consider it like having this kind of computation domain with the length L and the height H, where all the boundaries are artificial except the one on the strip. So you can see the dimensions of the domain mentioned here. It's really taken from the experiment, but it's just for demonstration, so it's not so much important. We did the simulation for 2 different speeds of movement. These were these 2 velocities, just to compare what will be the observed density and velocity field and so on. And here you can see the formula for the background density profile using the characteristic density we have in our model. There is some typical length scale which is set in this way. And you can see that the parameters are really close to water parameters. So we can do the simulation on this. So this is the summary of the computational test case. We have the domain omega. And instead of having a moving domain, we prescribe a fixed velocity on the inlet. So this is the constant velocity prescribed at the inlet. And otherwise, the only physical boundary conditions we have are around this strip where we prescribe the no-slip condition for the velocity. Otherwise, we don't know almost anything except that we want to simulate some kind of non-disturbed and fully developed flow and so on. But it's important to know that all this boundary is just artificial and it depends on the choice of the person who is doing these simulations, how far from the physical object it will be. So we are trying to impose some conditions that will be, let's say, soft in the mathematical sense, that they will not affect strongly the solution. So this is the computational setup. So what is important to mention is that what we expect, we have some constant velocity profile at the inlet boundary. Nothing is almost happening until the fluid will reach this moving strip. But then, because of the no-slip condition on this strip, it will generate some perturbation to the flow, because suddenly the fluid has to stop on the surface of this strip, which will generate some vertical perturbation to our velocity field. So even if this object has a zero thickness, theoretically, it will generate a significant vertical perturbation to our flow field. If you take a look, too fast. If you take a look, so these are the contours of vertical velocity component, where you can see the strip is just in this area. The length of the strip is 2.5 centimeters, so it goes up to 1/2 of the length of this square. So you can see we first have some, because the fluid has to stop on the strip, we have some vertical perturbation up of the fluid velocity, and at the end of the strip, we have the same kind of perturbation down. But typically, if you will have a non-stratified flow, you will only create some boundary layer in the close proximity of the moving strip. But here in the stably stratified flow, it will generate a huge wave field. This, you can really see the result of computation, where even if the thickness of the strip is 0, then you can see how far these waves generated by this moving strip are going. It's somehow similar to waves on the surface of a lake, for example, if you are moving a ship over the surface of the sea, of the lake. Here you can just see again, the only difference between the two simulations is in the velocity of the strip, where you can see still the wavelength of those waves generated by the strip has increased with the speed as expected from the relations given before. But so you see, it generates a very nice but non-trivial wave field even from this very simple geometry. What is important is to see that even from this very, very small obstacle in the flow, it affects the whole domain, not just the close neighborhood of the object, as we are used to from some engineering calculations of some, for example, flow over airfoil or something like this. But still, this is just a small portion of the whole computational domain. You might have seen that I've defined quite a large computational domain. So if you continue, you can see it goes even further. This is just this is just the magnitude of the two components of the velocity vector. U is the horizontal, W is the vertical, and you can see that really, if you go away from the leading edge of the strip, you can see the amplitude of the oscillations is diminishing slowly, but really slowly, but the wavelength remains the same. This is what we have seen in the picture. What is interesting is to see the whole computational domain, and really you can observe that the oscillations generated by this very small obstacle really affect the whole computational domain, and it doesn't really matter how large your domain will be. For example, here you can see there are now the contours of horizontal velocity and pressure before we have seen the contours of the vertical velocity. So you can see that you have there some strong waves generated close to the obstacle, but aside of this, you can see that these waves keep propagating up to the boundary, where you can already see some boundary effects due to artificial boundary conditions that we will discuss later. But what is also surprising, at least for me, it was that even from this very small, still the obstacle is just somewhere here. And all these artifacts will propagate upstream up to the inlet boundary. And even for the, let's say, the horizontal velocity, because these are the components, these are the contours of the horizontal velocity, it will generate very interesting and important wave structure up to the inlet. So not just behind the obstacle, but it goes back up to the inlet. And even more strange, it's for pressure. Again, you can observe some wavy pressure patterns here, but the region of the high pressure, again, from some object that is small as this, propagates up to the inlet boundary. So this will be one of our major problems, that even very small obstacles will generate some phenomena that will propagate and cover the whole computational domain. So no far field boundary will be far enough to be free of these physical phenomena. Let me just discuss briefly some of these problems that we were facing in these simulations. The major problem is that if you take a computational setup that you are used to from the non-stratified case with constant density, then typically it will not work. It will cause you more troubles than numerical results. So here, for example, these equations, so here we have just one physical boundary, which is this one. This is, let's say, a no-slip wall on which we prescribe the no-slip boundary condition for velocity. Inside of the domain, we have the continuity equation in the sense that this is the divergence-free constraint in 2 dimensions, and this is the transport equation for density. And now just try to think in consequences. What will happen if you prescribe some what you believe is a soft boundary condition? So, for example, on the inlet, we typically prescribe the velocity profile for the horizontal component, and we set the vertical component equals 0. But if you introduce these two information into this equation, then you will immediately get back that you have to prescribe or naturally satisfy that the horizontal derivative of the density should be equal 0. So no change in the density across the inlet boundary. But because the transport equation in general for density is of hyperbolic character, so you cannot prescribe just the Neumann condition for the density. You have to really prescribe the values of density on the inlet. But it's even more strange on the other boundaries. For example, at the outlet boundary, typically what the people used to prescribe is, let's say it's fully developed flow. It's so we prescribe the horizontal derivative of the horizontal component to be equal 0, but then if you plug it in to this divergence-free constraint, then immediately it will tell you, okay, but then your vertical velocity component must satisfy this equation. And because you have prescribed the 0 velocity on the wall, so it means that on the whole wall, well, it's not a wall, it's a boundary, on the whole outlet boundary, by prescribing this condition for the horizontal component, it will block all the vertical velocity. So if you want to satisfy your equations up to the boundary, this artificial boundary, then the result will be that the vertical velocity will be equal 0 on the whole boundary, which is very unfortunate for our wavy velocity field. The same story is on the upper boundary, where typically you prescribe that the vertical velocity component derivative in the vertical direction is 0, so it's not changing. But then again, if you plug it in the divergence-free constraint, this will imply that the horizontal derivative of the horizontal component must be 0. And again, if you prescribe some velocity profile at the inlet, so it means that the horizontal velocity along the whole boundary will remain constant, exactly. Otherwise, simply the divergence-free constraint is not satisfied. So, and again, it's maybe okay for some non-stratified case where this boundary is really far away from the obstacle, but as you have seen in the previous example, we cannot afford to have this kind of boundary, far field boundary conditions because they are really too strong. So what we call a soft boundary conditions for the non-stratified case is not soft enough for the stratified case. The velocity and density boundary conditions are strongly coupled, which we will see on the next slide. And sometimes there is some, you are getting a controversial offers for the boundary conditions which do not comply with the character of the governing system. This is another example of how it's complicated in the stably stratified flows. Here I'm considering almost the same case as before, just now taking closer look to the momentum equations. So these are just momentum equations written in the Boussinesq approximation in 2 dimensions. And you can see 2 colors here because I'm considering like fully developed flow over a flat plate. Then all these black terms will disappear because they will be equal 0. I mean the time derivatives because it will be steady. Then it's fully developed, so all the horizontal derivatives will disappear. The vertical velocity will be equal 0 and so on. The same here. These guys will disappear and only the blue terms will remain. So this is what I've written here. So if you take a look on these remaining terms, what has remained from your equations, so it's telling you something about the gradient of the pressure perturbation. But now if you take the partial derivatives here with respect to z, here with respect to x, to create the mixed partial derivatives, pxz and pzx, that should be equal, the mixed second order derivatives, you will end up with this kind of relation that must be satisfied between the density perturbation and essentially between the velocity profile. And it simply says that if for the velocity profile that you have chosen or obtained from the physics, its third derivative is non-zero, then there is absolutely no chance to have fully developed flow, and the density perturbation will change along the horizontal direction. So simply imagine the situation that, for example, here on the inlet, you will prescribe some velocity profile that you are happy with. And based on this, you may figure out that in your velocity profile, if the third derivative is non-zero, which typically is not, unless it has some special form, then you will never get a fully developed flow. So already from the very beginning, when you are trying to set up the computational test case, you must be very careful about what you are prescribing at all boundaries, essentially, because it's very, very sensitive. So here just I concluded in this that the wrongly chosen inlet velocity profile can generate some density perturbation, and then consequently some vertical velocity perturbation. So we have to be very careful, and you will see that this kind of phenomena really appears in numerical simulations. When you take a closer look at this dilemma concerning the inlet velocity profile, for example, I had a problem with some of my simulations because I've chosen this kind of velocity profile, some variable velocity profile up to certain height, up to here, and then continued by a constant velocity, which is typically what is done in the engineering applications. But then the problem is that if you now do previous analysis, that you need some velocity profile that has a third derivative equals 0. So it essentially says it must be of a parabolic type velocity profile, where because of the no slip condition, you will cancel out this term. So you will choose some parabolic velocity profile here up to this point. It seems that you can be happy with this, but then if you prolong it by a constant, but constant is again just a, let's say, degenerated parabolic profile, then it doesn't work. Simply, if you take a look at what is happening in your case, so it means here you have the original velocity profile, here you have the first derivative, which is linear here in this second order parabola region here. This is the second derivative, which is constant, and then this is the third order derivative. So it's true that piecewise, even if piecewise this part is parabolic and this part is parabolic as well, then if you glue together two different parabolas and calculate numerically the third order derivative, then you will see that there is some kind of a non-zero value here at the transition point. And already this is enough to completely destroy your simulation, because then at this point, starting from the very beginning, from the inlet of your computational domain, you will start to generate some density perturbation and consequently also the vertical velocity perturbation. So then all the simulations will depend on how far is your inlet from your object of interest. So we have to be very careful, and even this kind of trivial choice of inlet velocity profile is inappropriate in most of these simulations. Here's some summary of the numerical method that I was using in a majority of my simulations. We will go into detail in some of these main features. So we were using the time marching technique. So it means everything was formulated like for unsteady case, but then the steady limit was sought by numerical iterations. We have used the artificial compressibility method, which means modified divergence-free constraint by adding a pseudo time derivative of pressure. Again, this is a term that will disappear at the steady state, so it's not so essential for the simulations here. We have used the semi-discretization, so it means method of lines. So we separated the space and time discretization to have, let's say, wider choice of each of these discretization methods. For the space discretization, I've used here for the simulations that I will present the compact finite difference space discretization, which has a very high formal resolution and keeping rather compact computational stencil. Then to avoid some non-physical oscillations, I've used the strong stability preserving Runge-Kutta time-stepping method. It was previously called a TVD Runge-Kutta method, which is, let's say, kind of time integration method, which doesn't introduce any extra numerical oscillations. And finally, to make sure that only the physical oscillations will be preserved in the computational domain, I've used some kind of low-pass filter stabilization. So it means to filter out everything that has the grid frequency. Now let's take a look a bit more into detail on the numerical methods. I will go here a bit faster than in the previous slides to save some time. I think everybody is familiar with some basic numerical methods where, for example, to approximate the derivative of a certain quality at some nodal point, we can approximate it using the so-called divided differences. Here it's written in the central form, so we take 1 point on the left from our grid point, one value from the right, and we divide by the distance between the 2 points. This is the standard way. You can get the second order approximation if you do just this trivial replacement like this. But more general formula says that you can make a weighted average with this kind of weights between the divided differences over larger and larger computational stencils. Using this, for example, if you take these weights 4/3 and -1/3 for the larger one, you can get approximation which is of higher order than before. So this is a rather trivial task. The problem is that such approximation that can in general be written in this way. The good point is that it's really explicit. You want to know the approximation of the derivative. All you have to do is to make this kind of weighted average of the divided differences. So if you write it in a matrix form, it means on the left-hand side, you will have an identity matrix. And here you have some, let's say, multi-diagonal matrix, which has certain nice properties and just certain number of non-zero elements that are just along the diagonal. But in general, it's just a formula for a calculation of the derivative. The problem is that with this kind of approximation, if you want to get something more accurate than the second order, then the computational stencil is getting bigger and bigger. So you can see that for order 4 approximation, you need 2 points on the left and 2 points on the right. So already 5-point computational stencil, and going to even higher order, 6th order, it's even more strange. Here there is a mistake. It should be -3 and +3. So you can get a 7-point computational stencil here. So in general, these methods are nice because you get explicit formulas for the approximation of derivatives, but the drawback is that you need quite a lot of grid points. So it means large computational stencil to get higher order approximation. So this approach can be generalized, and this is what we do in the so-called compact finite differences or compact approximations, where instead of only approximating this single value of the derivative by this weighted average of divided differences, we approximate at the same time some linear combination of derivatives by linear combination of divided differences. It seems to be a little bit strange, but first, the classical finite differences are hidden in this case for special choice of the linear combination on the left-hand side. But the advantage of this approach is that to achieve the same order of accuracy, you may need a smaller computational stencil. Disadvantage of this approach is that instead of having just the one unknown value on the left-hand side, there is some linear combination. So it means if you write it in the matrix form, you will have some not just unit matrix on the left-hand side, but you will have some diagonal, multi-diagonal matrix on the left-hand side and the same on the right-hand side. So to get finally this vector of unknowns, you have to invert this or to solve this system of linear algebraic equations. So it's not just formula, you have to solve a system of equations. So this is a drawback. This is the price you have to pay for getting some more convenient approximation. For example, here, this is example of the case where on the left-hand side, we will obtain some pentadiagonal matrix where not only the main diagonal will be full of units, but the off-diagonal elements will also have some non-zero values. And on the right-hand side, there is still the linear combination of the divided differences. But again, so you see, you have pentadiagonal matrix on the left, and you will have like seven diagonals on the right-hand side. And different choices of the coefficients, coefficients A and coefficients alpha, which are the weights of derivatives or divided differences, will give you different numerical schemes. So the implementation is quite straightforward. It's just about the change of coefficients, and you can get different schemes. Here, this is just a table with a summary of those compact finite difference schemes. You see these values of coefficients A1, A2, and so on. If you want to achieve certain, let's say, order of accuracy for the scheme, you have to set properly the coefficients. So for example, what is important for us for a numerical solution, we don't want the pentadiagonal system on the left-hand side because we know how to solve easily and efficiently these three diagonal systems. So we will focus only on the schemes which will have three diagonal metrics on the left-hand side. So it means that the A2 coefficient should be always set to 0. And then we will only have one coefficient on the left-hand side. And based on this, we can get different families of schemes with different properties. Here, what it says is, so we will focus on three diagonal methods. So we will always have to only invert a three diagonal system. And this is about the size of the computational stencil on the right-hand side. And you can see that we can, depending again on the computational stencil, we can get different order of approximation for the derivatives. So what is nice is to see that, for example, in the standard finite differences, you have seen that we can, on the 3-point computational stencil, we can only get the order 2. But here we can increase it at the price that we have to invert three diagonal system. The same for the classical finite differences. On the 5-point computational stencil, we can only get the order of approximation 4. Here we can go higher. So it's a very nice feature to have for, let's say, this kind of high resolution methods when you want to resolve what we have seen in our computational field, the small amplitude waves, but in the whole computational field. So this high resolution is very important. And because of the implementation of the boundary condition, we want to keep the computational stencil as small as possible. So typically what we are using are these kinds of numerical methods where we have the computational stencil up to 5 points. This is somehow manageable at the numerical level for the kind of problems that we are solving. Before I will go to time discretization, I would like to mention this case of low-pass filters, because in the same way as the approximation of derivative by divided differences, we can let's say smooth. If you take this like kind of a noisy signal, so we can smooth the signal by taking, let's say, the weighted averages over larger and larger computational stencils. So by this averaging, you can get some smoothing factor into evaluation of these new values. And again, to reach some order of approximation and to avoid over smoothing, it's good to have a larger computational stencil. But again, the same as for the approximation of derivatives, if you want to keep it compact, you can, using the same trick as we did for the approximation of derivatives, and you can employ the so-called compact filters. Again, the structure is exactly the same as for the approximation of derivatives before. So you are having the weighted averages on the right-hand side of your system, but then you have to, again, invert some system for the new filtered values denoted by this little hat here. So we will take the weighted average of the non-filtered values, and we will obtain the filtered values out from the solution of, for example, this kind of three-diagonal system again. So it's good at the level of the solver that all you have to know, in fact, is to solve three-diagonal systems. And you can live with this and solve quite complicated three-dimensional cases at relatively high resolution. These are the coefficients for this kind of filters. You see there exists a whole families of filters, and you can really adjust it. What is important is that you can obtain the appropriate, let's say, spectral response of the filter depending on the kind of the filter and some tuning parameter. So the filters are denoted filter 2, filter 4. It has something to do with an order of accuracy of approximation of some functions, but it's not so easy to explain what the order is. But what is important for us is the spectral characteristics of this filter, which simply says it's a low pass filter. So here, this is, let's say, this transfer function can be kind of amplification factor for the amplitude of the signal. So you can see that for the low frequencies, nothing is happening. And just for the high frequencies, the amplitude is selectively diminished. So this will allow me, if I will choose certain filter and some parameter to adjust the filter, I can really set almost perfectly the low pass characteristics of that filter. So it's, in some sense, it's better than the standard, let's say, numerical diffusion that is applied to everything. Here it's applied selectively to high frequencies only, where you can really tune it up to only, let's say, damp the grid-like frequency, which is typically associated with numerical oscillations. Here is just brief summary of the time discretization. It's a kind of non-standard Runge-Kutta method, so it's a multi-stage method. Here I'm giving some references for this family of strong stability preserving SSP Runge-Kutta methods that are written in some special form, but it's nothing else than a Runge-Kutta method with some special choice of coefficients. So first we discretize in space using the compact finite differences. This is this space discretization operator. And then we perform the numerical time integration using this multi-stage SSP Runge-Kutta method. You can find the details in the references given here. These are the standard SSP Runge-Kutta methods. There is a whole family. Here it always stands SSP-SO, its number of stages and the order of accuracy. So one stage first order method is just the Euler method. So it's again special kind of Runge-Kutta, and the modified Euler method is SSP-22. Again, you can write it using these coefficients. What we have used in our simulations and what is from all the methods mentioned in all those papers given before, this one, this SSP-33 works best. It was a bit surprising because we were expecting to use some low order method. This is third order in time, but we have steady case simulation. So we were looking for some method which will be of first order, which will have much larger CFL number here. But finally, for the nonlinear problem that we are solving, it has turned out that this SSP33 method performed much better than the method that we were expecting to use. So the good point about these SSP methods is that if you don't introduce numerical oscillation by your space discretization, then this property will remain preserved by this time integration. Because otherwise, if you choose improperly the time integration method, then you can introduce the oscillations in your solution just by wrong time discretization. Now we are coming to flow over hill, which is the most important physical example that we are calculating here. Again, we are mimicking some kind of laboratory experiment which comes from this paper. I think it's already from 80s, and some recent numerical simulations mentioned here. Here you can see essentially the setup. So it's a single rotational symmetric hill of this shape. It is this inverted polynomial shape with this kind of quite large computational domain. So it's not a big surprise. This is the remaining part of the computational setup, because we are working with, let's say, boundary layer type of flow under stable stratification. This time we have chosen the linear background density stratification that is given here. Unfortunately, it continues on the next line. So it's really, let's say, some characteristic density, which was chosen as the density at the height of the top of the hill, and then plus gamma, which is a constant, times the distance from this height level. This will give you the linear density profile, and together with this, we have, of course, the gravity acceleration that goes against the z coordinate. This is why there is the minus sign, and otherwise there is some standard velocity profile with some no slip boundary condition close to the wall. Okay, so this is the basic computational setup that is important for our considerations. What is important is the characteristic velocity, which is again the velocity from the inlet velocity profile taken at the level of the top of the hill, and the characteristic density taken from the density profile at the height of the top of the hill. And it's really a laboratory scale, so the height of the hill is like 2 centimeters, and again it's in a water tank, so it's close to density of water. Then this is the list of simulation parameters. Why it's written in so complicated way? Well, because to characterize the stably stratified case, we typically use 2 non-dimensional parameters. One is the Reynolds number, which everybody knows the definition, and the second is the fruit number. Both of these similarity numbers, unfortunately, depend on velocity. So, for example, if you want to simulate the effect of the change of the fruit number, you can, but then it depends which parameter you are changing, because if you would like to simulate the different fruit number flows by changing the velocity in your computational setup, then it would mean that you will automatically also change the Reynolds number. And this is something that we would like to avoid. So we are always looking not just to change in some non-dimensional parameter, but we really take care about what physical parameters we are changing in the numerical simulations. So here you can see that we are always speaking about the, in the table, you see this is the table of the fruit number, and it's changed using either velocity or the background density gradient. So these are the two physical parameters that we are changing independently to achieve different Reynolds number and different fruit number. And it's really important because many people say that, okay, there is some similarity, and for the stable stratified flows, the fruit number is the dominant similarity parameter, so it's the most important one. But from the simulations that we have done here, it's true that there is some similarity because of the fruit number, but the Reynolds number is at least as important. Here what you can see, we will show almost all the results in terms of the contours of the vertical velocity field. So here, let's start from the top. Fruit number equal infinity means no stratification. It's like background density gradient is equal 0. And this is typically what you can see what is happening with the vertical velocity in case of no stratification. So there is some kind of a bubble inside of which the vertical velocity is different from 0, but otherwise from this very well localized space, nothing is happening. Really, the flow remains attached, and there is no huge wake, no waves, and nothing. If you just increase double the velocity, then you can see some significant wake behind the hill, but otherwise it's still very well localized. It's just behind the hill, close to the wall, but otherwise in the whole computational domain, nothing is happening. If you increase even more the inner velocity, you can get more, let's say, bigger wake, which can potentially get unsteady, but still it's a standard what do you expect from a flow over a hill. So otherwise, you can see that in the large part of the computation domain, nothing is happening. But if you increase the stratification, so the fruit number will be essentially finite, you will get a completely different picture. So here you see, here the density gradient was always 0. But here, the density gradient is changing, but the fruit number remains the same. This is because if you want to increase velocity, then you have to compensate to get the same fruit number by changing at the same time the background density gradient. What is important here, there are two things. First, you can see that for the stratified flow, you can see some wave structures behind the hill going up to the top of the computation domain. So it's not just localized, goes to the wall, but it goes up to the upper boundary. And really here, the flow goes up, down, up, down, up, down. It's really wave pattern behind the hill, but not just in the boundary layer, but up to the top of the computational domain. So this is the first observation. Second observation is that depending on the velocity, of course, the wavelength of those waves, because of the identical fruit number, this seems to be the same. But otherwise, there are some features that are rather velocity or Reynolds number dependent. So here you can see that there is no problem for high velocity at the inlet, but for low velocity, the same fruit number, you already have some strange feature on the inlet. And the same is true for even higher stratification. You see that the frequency of those waves is increasing. For the same fruit number, the frequency is the same, but some other features are not similar. Namely, these strange features goes to the inner boundary. And evidently, if you calculate the same case, the same hill, the same grid, the same density, the same velocity in the non-stratified case, you have no problems around the boundaries. So it's let's say the stratified case is much more complicated. This is how looks the, let's say, the velocity field close to the ball. And again, but you can observe the same fruit number, but you can see the structure of the wake, the recirculation behind the hill is very different. So the size is very different, even for the same fruit number. The size of the recirculation zone becomes very different. You can see that the size of the recirculation zone is rather related to velocity, so it's rather related to Reynolds number. It's not exact, but as you can see from the next slide, it's even more pronounced for the lateral side view of the same phenomena. So if you compare the cases with the same fruit number, you see the same wavelength of the waves behind the hill. But what is interesting is the structure of the recirculation zone, which is very well visible here. You see there is a massive recirculation in this case, but the recirculation is very flat. So if you look at it, so it's really confined to the boundary layer, and above this boundary layer, you don't see any recirculation. So the recirculation is not just size in length, but the thickness of the recirculation is what differs from one stratification to another. So what we have seen here is how it's very much sensitive, all these stratified cases sensitive to boundary conditions. There are some non-physical effects due to artificial boundary conditions. You see the influence of these boundary conditions at a very long range. So if you set something badly on very distant boundary, it will propagate in your flow and it will spoil the whole simulations. Let me point out just the last point, because you should understand the boundary conditions in these three ways. There are some physical boundary conditions that physicists will tell you, okay, in the far field, for example, this and this component of the flow will disappear. But this is physical, which doesn't always correspond to the nature of mathematical model. We already spoke about it. For example, if you have some hyperbolic equation, then you have to prescribe something at the inlet, but you cannot prescribe anything on the other boundaries, even if the physics tells you that it should be true. And the last level are the numerical conditions, because even if mathematician will say, you don't need any boundary condition at this boundary because of the mathematical nature of the governing equations, then numerically at that grid point, you must have some value. So how do you get those values? So there are some numerical boundary conditions. This is the standard computational setup that we have used in the simulations before. But let me point out rather these. What we believe is a soft boundary condition is the extrapolation. So it means you do the linear extrapolation of the quantities, which is what we believe is the softest possibility. But you cannot use it for all the quantities. Typical problem is at the far field boundary, which by this I mean this top boundary. Problem is that because of the wavy structure of the flow field, there are certain parts of the boundary where the flow goes out and some other parts of the boundary where the flow goes in. So technically speaking, if you want to prescribe something on the inlet, then be aware of the fact that there are some parts of the other boundaries that also are inlet boundaries. So it's very complicated to prescribe something on this, what we call the far field or free stream boundary, because we a priori don't know if it is inlet or outlet boundary. It depends on what kind of wavy pattern will develop in the domain. And we can never put it far enough from our obstacle, which is just somewhere here. As I said at the beginning, if you have non-stratified case, the flow will just go around the hill. And here at the top, nothing is happening. So it's relatively easy to prescribe something there. But for the stratified case, we cannot do this very primitive assumptions on the flow. So it's complicated. This is how you get it when you try to solve these three-dimensional case. So except this, this ball, sorry for the line, on the wall, this is the only physical boundary. All the other boundaries are artificial. So you can choose it at arbitrary distance, technically. And you are looking for some compromise between the distance and the accuracy of your simulation. We don't have a priori defined what is inlet, what is outlet. We don't know. What is also strange is that because of the velocity vector, I mean here at the free stream boundary is almost parallel to the boundary, which is also causing some problems. And of course, far field boundary is never far enough. Typical problem is, for example, if you use the grid for simulation that comes from the standard numerical solver, where the people believe that just close to the boundary, you need fine grid points. And if you go away from the boundary, that you can have more coarse grid. That's true, but not in stratified case. In stratified case, because some physical phenomena appear close to the upper boundary. So if your grid is coarsened towards the outer boundary, you will miss certain phenomena, and then all the simulation is spoiled. So this is kind of simulations that we did. So in order to assess the effect of the position of the artificial boundaries, we did simulations on bigger and bigger domains. So let's say for the set of simulations that I will be showing here, this is the big computational domain on which we get some reference solution. And it's really for a reference. So this is the complete solution on the whole computational domain. Then we just take a portion from it on some smaller domain and try to repeat the simulation, the same case, just on this smaller computational domain. And then to compare what is the effect of this so-called artificial boundary conditions on the artificial boundaries. And this is what you can see typically, and this is what was a big problem. So here on the top, you have the simulation on the whole computational domain. And this is what you get for the vertical velocity. And this below is just the smaller computational domain, but we have used on the top boundary for the free stream boundary, saying that the pressure is not changing across this boundary. So dP over dN equals 0, so which is just a numerical artificial condition to be used. But then what you observe for the vertical velocity is that this, what we believe is soft boundary condition, will completely block the vertical motion of the fluid in the domain. And what you obtain is quite far from what you obtain on the bigger domain. So the choice of artificial boundary and the boundary condition on it will have severe impact on the numerical solution. Here you can see the same from the 3D point of view, but the information is the same. This is the truncated solution, so solution on some bigger domain that we just cut off and show on a small portion of it. And this is directly computed on the smaller domain with some artificial boundary condition on the top. And you see that these solutions are not really very much similar. And it's getting even worse. If you look, the same problem is not just on the top boundary, but also on the lateral boundaries, where if you truncate the original solution, you see that there is some flux, fluid flow through the lateral boundaries, and there is nothing if you employ the lateral homogeneous pressure boundary condition in this case. If you look at the isosurfaces of the vertical velocity, it's again even worse. So this is what essentially this is what you want to get, and this is what you obtain. So you see that these contours are quite far away from each other, and everything just depends on the choice of the position of the artificial boundary and the condition, artificial condition on this artificial boundary. The same story is for the transversal velocity component and the fluxes through the lateral boundaries. Of course, we were not the first one to face this problem. It's very well known, the choice of artificial boundary conditions for the non-stratified cases. And you might be familiar with the so-called do-nothing boundary condition, which naturally appears in finite element formulations. And it can be formally rewritten in this way. It's associated with the work of Rolf Ranacher, John Haywood, and Stefan Turek in the 90s, and it's very often used in non-stratified case. But it's not always perfect. It was somehow improved and generalized recently in 2014 in this paper by Brack and Mucha. And they call this condition directional do-nothing condition because there is some condition depending on whether the flow is going inside of the domain or outside of the domain. And there might be some correction term associated with the, let's say, balance of kinetic energy. But none of these approaches is suitable for our case. Imagine in our case, we are moving close to the outer boundary where both the viscosity is close to zero and this is also close to zero. This would mean that we will have to prescribe the constant pressure along the boundary. And here it's almost the same. So these conditions are not suitable. They are too strong and too restrictive for the case of stratified flow, where you have too many wavy structures in the flow field. So we have proposed some new boundary condition that works in a different way. Officially, it's called convective pressure derivative condition that will be referred to CPD condition in the following simulations, but non-officially we call it the do something condition, in contrast to this do nothing condition, because this really does something. It's a condition that we want to prescribe in the far field for the pressure. So it has the structure of the Neumann condition for pressure, but non-homogeneous Neumann condition, where this function can be evaluated pointwise at every point of the boundary. If you take a look, so again, the same case solved as before. This is the reference solution from the bigger domain, just truncated to a smaller size. So this is what we want to get, essentially. This is what you get with the standard approach with the homogeneous Neumann boundary condition for pressure. And this is what you get with the new boundary condition that we have proposed. So evidently, what you can see, what is the most important, that you can see non-zero vertical velocity on the top boundary. So we allow the flow to pass through the boundary in both ways, which is good. If you look more into detail, we can impose the same boundary condition on the lateral boundaries, exactly the same condition. And again, this is the reference truncated solution. And this is the new solution obtained using the new boundary condition. It's very different from what you get from the standard approach, where this homogeneous Neumann boundary condition blocks all the flow through this part of the boundary. So the new boundary condition performs much better, which is also visible here. Again, this is the standard boundary condition, homogeneous Neumann condition. This is the reference solution that is almost what we want to get. And with this new boundary condition, we are getting something that is very much similar. Definitely more similar than what you get from the standard approach using the homogeneous Neumann boundary condition. That's really very far. We can do the same comparison. It's even more apparent here. You have isosurfaces of the vertical velocity and it's truncated to the smaller domain. So again, this is the reference solution we want to get. This is the bad one that we get from the homogeneous Neumann. But if we employ the non-homogeneous Neumann, but with properly adjusted the right-hand side of the, instead of 0, to adjust the pressure gradient across the boundary, then we can get something that is much more useful. We did the tests with different position of the artificial boundaries. So again, this is the original solution. Where here on the left, you have always the original boundary condition for the homogeneous Neumann boundary condition for pressure, which you can recognize in the pictures that the contours of pressure enter perpendicularly the boundary. So this is, let's say, the reference solution, and we are always interested just in the color part on the bottom of your computational domain. So you see that in the original approach, we have chosen 3 different computational domains. Otherwise, the cases were exactly the same. And we were looking how the, let's say, the height of the computational domain will affect what is happening inside of the domain, let's say in the region of interest, which is around the hill. And you see that if you move the artificial boundary closer and closer to your object of interest, you are getting always very different results. You see, for example, this feature you can only observe here, but it's far from what you get here. You see, and it's the same like at this position if you compare it. So if you really want to get some relevant results using the original approach, you must have a quite large computational domain, because all these non-physical phenomena will be happening quite far from your object of interest. With the new boundary condition, first what you can see, really the angle at which the contours are entering the boundary is non-zero, so it's really non-homogeneous boundary condition for pressure. But what is more important is that, for example, if you compare this result with this one, so, and you really look at the region of interest, that there are not so big changes like you have observed using the old approach. So the new boundary condition really minimizes the effect of the far field boundary condition, and it's definitely much better than the original approach. It's very important for the people, for example, who are doing the weather prediction, because then, for example, if you count the computational points and the price you have to pay for the numerical simulation, then it means that it doesn't almost matter if you take this domain, which is just half of the size, understand it, half of the price of the simulation on the larger domain. So using better boundary condition can give you the opportunity to obtain your results faster and cheaper, of course. So the new boundary condition behaves very well. Here is the same, let's say, demonstrated on the other components of the velocity field. Again, 3 different heights of the domain. And you can observe that the differences from one size to another are much larger for the original boundary condition using the homogeneous Neumann condition than for the new, let's say, do something condition, which is the convective pressure derivative condition. It's the most apparent is on the vertical velocity contours, where you can really see that by using these homogeneous Neumann condition, there is always something wrong happening close to the far field boundary. But for example, the difference between this picture and this picture, there is not a big difference if you look at the contours here. They are almost the same. Just this lower result was 25% cheaper and faster because we can cut off this upper layer of the computation domain. And it continues up to this even smallest computation domain. So it really works very well. I'm just finishing by the discussion why we believe it works so well with this new boundary condition. So this is the formula that we have for this boundary condition, this non-homogeneous Neumann condition. So there are, let's say, two parts of this boundary condition. This is the first part, and this is the really essential part. This is normal, let's say this is the derivative of the normal component of velocity with respect to normal direction. So we can impose the same boundary condition on all boundaries of our computational domain, essentially, but it was meant for the upper boundary, where this will be vertical velocity component with respect to vertical coordinate. But the same was imposed on the lateral boundaries, and the same can be imposed, as we will see later, on the inlet boundary and on the wall. We can use the same condition everywhere. This term is really essential. We are trying to understand what's the meaning of this term, and you can really understand it if you introduce some, let's say, local coordinate system. So you have some boundary, then here somewhere you introduce a coordinate system that will have some tangential part and some normal part. And then you will apply your boundary condition. So let's say that we have this divergence-free constraint, and let's say that this z direction will be associated with the normal component. So let's say if the normal derivative of normal component, which is exactly this one in our local coordinate system, if this will be 0, so what it means, what you will get, do I have it? Yes. If this normal derivative of normal component will be equal 0, then it means that in the tangential plane, the two-dimensional divergence-free constraint is satisfied. So the flow is like locally two-dimensional. So let's say that this normal derivative of normal component, velocity component, is kind of an indicator indicating if the flow is locally two-dimensional in the tangential plane, or if it is not. So if this derivative will be 0, so it means that the flow is two-dimensional, and the flow lives just in the tangential plane, so there is no reason to have some pressure gradient across the boundary to enhance or suppress the flow across the boundary. So this is kind of indicator if we should apply some pressure gradient in the normal direction. Then the second part is just a scaling factor. It's characteristic density times the magnitude of velocity. And it's important in the momentum equations because close to the outer free stream, the viscous terms do not play any important role. So it's the convective term that plays the major role and is somehow counterbalanced by the pressure gradient. And this is why to achieve the appropriate scaling of this, so to do not exaggerate this pressure gradient, it should be scaled as the convective term in your momentum equations. And this is done in this way. It's really important to have the density there, and it's important to have the magnitude of velocity, because one of the features is that it's also invariant to the shape of the boundary. Not just shape, but orientation of the coordinate system. So we don't play with components, it's the magnitude of velocity. And as you have seen, it works very well in this case. Any deviation from this scheme seems to cause more troubles than positive effects. And we are finishing, it's already too late. As I said, this do something condition was originally meant for the far field or for the lateral boundaries. But if you take a look what will happen with this boundary condition on the no-slip wall and on the inlet, it's written here, but let's say on the no-slip wall, velocity magnitude will be 0. So on the no-slip wall, it will degenerate in dp over dn equals 0. So you will get the standard boundary layer approximation where you have the normal derivative of the pressure will be equal 0. So there it doesn't bring anything new, but you can use it. The same condition as you have for the far field, you can use also on the wall. Surprisingly a little bit, it's the same on the inlet boundary. I don't know if you can imagine this kind of situation, but imagine on this boundary, you have, for example, u equals some u0, and the w, which is the vertical one, is equal 0, and the v, which is the transversal, is equal 0. So in this case, it can be shown using the divergence-free constraint that here this ux must be equal 0, which means that in the previous boundary condition, this normal derivative of normal component will be identically equal 0 on the inlet. So again, you will recover the homogeneous Neumann boundary condition at the inlet. So you can really use this do something condition on all boundaries except the outlet for non-stratified flows. For stratified flows, for non-stratified, you can use it everywhere. And it's really a soft kind of boundary conditions. Of course, the last comment is that everything depends on the how do you treat the velocity. As I said, what we have used is the extrapolation of all velocity components, which means the linear extrapolation. Maybe there exists some better choice, but this combination of really extrapolation of velocity and imposing this do something condition on pressure and doing this on all boundaries, it really works. And even for the stratified flow case, it gave us the best results so far. And this is everything from me. So thank you for your attention. And in case there will be some questions, I will be happy to answer them.
Yeah, thank you, Tomasz, for this very nice and interesting talk. It was very nice to see your presentation on or your insights of your recent research. I think we have time for 1 or 2 questions. I don't see any questions in the chat box right now, but maybe if you have questions, please unmute yourself and ask your question. I have a question regarding slide 32. Can you please go back to slide 32?
I can try to. The numbering is a good thing. This one. 32.
Yeah, that one. The upper left panel. Here we have the no stratification case, right?
Yes.
I would expect that we see an asymmetric solution with respect to the position of the hill. Is that correct? Because you have the flow, let's say, coming from the left?
Yes, but let's say the bubble here is really asymmetric. It's just given by the values of these isosurfaces that the let's say positive velocities, which means the wind goes up, are much larger than those then slowly tends back to the parallel flow. So it's really asymmetric in the same way as it's asymmetric here.
I see. Yeah, okay. No, that's
it's
fine.
just given by the choice of, let's say, the contour values for these isosurfaces.
You mean it's only a matter of presenting the results, or is that a real
maybe
phenomenon?
it's better visible in the two. Don't know if this one in the 2D fields, like here. So you see this like going up. I think it's the same kind of a case. This is much stronger bent up than this one that goes down. So it
yeah,
it's just a feature. Maybe there is some small recirculation behind that makes the hill look like in this way. So I don't know, but it's really not symmetric.
Yeah. Oh, okay. Okay. Thank you. Let me check the chat box. Okay. So then I have another question. Let me see. Ah, yeah. What about gravity wave braking? Can you or did you simulate this already with your new code or your new boundary conditions, or can you see it in your simulations?
No, I don't see anything really. But brought me to this kind of simulation was the fact that if I look into some, let's say, numerical simulations of other people, then I see that there is always some kind of a problem. The people are only showing a small portion of the computational domain. And for example, claiming, okay, we stop the simulation before the problems from the boundary will reach the, let's say, region of interest. Or we employ some, let's say, dumping functions close to the outer boundaries, or like sponge zones, or this kind of stuff. I was trying to do it a little bit more, let's say, mathematically, and really showing the computation domain as a whole from the edge to edge. There are no extra points, nothing really show everything. Mm-hmm. And then you may observe this kind of problematic regions. I was really, for example, surprised that I haven't seen anywhere even the numerical simulation of the stratified flow over a flat plate. And okay, if you try to do it, it's not so simple as I have shown with the let's say inlet boundary profile. Even if you choose anything that is not parabolic, you never get a stationary solution. Yeah. So I was interested in this kind of local phenomena. But of course, physicists, they have different point of view in most cases, because they don't care much about these small details like mathematics, numerics, and so on. So they are happy if they get the results, nice results that are similar to what they observe in physics. But no, so no wave breaking, nothing like this. There is some intention to do some more simulations using these new boundary conditions on some more challenging cases. And also what is important, I understand how the condition works numerically. It works very well. I have some, let's say, physical explanation, what I explained about this tangential plane and the local two-dimensional flow and so on. But mathematicians, they have never seen anything like this. So they cannot really explain why the boundary condition should look like this and why it works. So we know it works, but we don't know why. And this is a bit, I can sleep with this, but there are some people who cannot. So.
I see. Okay. I think that is a good statement to come to the end of that very nice webinar. Tomasz, thanks again for this very nice and interesting talk. And to all, we wish you a very nice day or a very good night wherever you are in the world. And we close this session now. Thank you very much for attending our webinar. Goodbye.
Thank you very much. Goodbye.